So we're going to start now looking at a slightly different sort of scenario. Imagine, for example, that we have variable mass. Now, what would that entail? For example, Konstantin Tsiolkovsky was a Russian physicist over 100 years ago, was looking at this sort of problem, and he said, well, suppose you have a spacecraft, so it's out in deep space, how does it move? On Earth, you have a car or a horse or something, and they push against the ground to move. And then a ship, a sailing ship, the wind pushes on the ship to make it move. And then for a propeller or side paddle or any kind of motorized vessel, it pushes against the water to make it move. But how does spacecraft move in space? And so he realized the spacecraft would have mass and would have to shoot the mass out the back of the spacecraft. Now, just as the previous example, when the cat jumped from one thing to the other, you ended up with motion occurring. There was no motion to begin with. You ended up with motion occurring. You could do the same thing. If you wanted to get somewhere, so you've got, for example, a space station dock, and you have an astronaut here just floating in space, and let's put the astronaut in a spacesuit so they don't suffocate, and they're holding some tools. Then if they're just floating out here away from the space station and they're trying to get back, they can throw tools this way, and the momentum of those tools has to be balanced by the momentum of the astronaut moving back in that direction. And so the astronaut would eventually drift back to the space station. So Tsiolkovsky looked at this and said, well, if you spew gases at a high velocity out the back end of the rocket, that's going to have momentum going this way, which would give momentum to the spacecraft going this way. So it's not having to push against anything per se. It's conservation momentum by stuff going out the back end, and the recoil of that shoving the spacecraft forward. And so, but as it goes, the spacecraft is losing mass. And so he looks at this and said, well, how do we resolve this? Well, we know that we had already derived that dp dt is force. So if you're out in deep space and there's no other force acting on you, so the force, the external force, is zero. So this is our external force. So the external force is zero dp dt. Okay. Well, rate of change of momentum is zero. That means for the rocket, there's no change in momentum here. But the rocket is losing mass. The gas is spewing out. There's obviously something's, you got positive and negative momentum. So let's look at this a little more carefully. dp dt is the derivative of mv. Okay. So that would be dm dt times v plus m dv dt. Well, that's m dm dt times v plus ma. Well, ma is like force. So he realizes that this would be some kind of force acting on the rocket. Now the rocket here, it's spewing stuff out, so dm dt is negative because the rocket is losing mass. So to make this look positive, he puts it outside the equation, minus dm dt times v equals ma. So MA is going to be your rocket thrust. Okay, so I'm going to write it as the force due to the rocket. So this is the thrust due to the rocket. Okay, and this is minus dm dt v. Sometimes the rocket equation is written so that we say that RV, okay, equals the rocket thrust. Okay, and so this is your MA applying to the rocket, except the M keeps changing here. Okay, R is defined to be the rate of change of mass loss. Okay, so this is what is often referred to as the first rocket equation. Okay. Now, first thing you realize is first. That suggests there's another rocket equation. And so we'll talk about that. Okay, then and then we're also going to apply the first rocket equation to a problem. But I'll go ahead and spend a moment talking about the second rocket equation while we're here. For the second rocket equation, before I get to the second rocket equation, though, let me point out that we have minus dm dt v equals ma. Okay, so that's going to be rv equals the rocket thrust right here. That v right there, what v are we talking about? Well, we're out here in space and you're spewing stuff out the rocket. The v right here is going to be the relative velocity. So this is the exhaust velocity of the plume. So really we ought to be writing the first rocket equation as RV relative here equals the rocket thrust. Okay, so that's really the way we ought to be writing that. But remember, this is minus dm dt v relative equals ma. As your rocket is moving along, m is changing. That's not zero. This is the rate of propellant that you're expending. So remember, the rocket has fuel and oxidizer. It's burning and spewing out here. Or even a monopropellant rocket in which you're just spewing out one thing, dm dt is the rate of mass loss. So this is the rate of propellant being expended. V relative here is how the exhaust velocity. Now you can actually change the thrust by changing the throttling back, the amount of fuel that you're burning, or by changing the shape of your exhaust, which would then change the velocity of the exhaust. Either one of those would change the thrust by changing one of these first two terms up here. And so that's something to keep track of. But you then look at it and say, wait a minute, I want to find out how fast is it moving at some future time. Well, the problem with finding out how fast it's moving at some future time is that m is changing. If the stuff on the left-hand side of the equation is staying constant, in other words, you're using a constant propellant being expended, and so you're constantly using the same amount of propellant as going out the same velocity, then the thrust remains the same. But if mass is changing, acceleration has to change in the other direction. So that means you cannot say that the velocity is v naught plus at. Okay, that's not possible. So we got to figure out something else to do in order to figure out the velocity, because that's what the second rocket equation does for you. It figures out the velocity. And so that'll be our next lecture.